Hi everyone, thank you for joining. My name is Daniel and I'm here with Poe, and today we'll be talking about the acoustic imaging for electronics assurance. So in 1974, at Stanford University, they created the Scanning Acoustic Microscope, also known as the SAM, and this was one of the first tools that would be able to create an acoustic image. Now an SAM consists of a transducer that produces acoustic waves, and then our focus with using an acoustic lens onto a sample where those waves are then either absorbed, reflected, or scattered at different angles with detectors either on the top or the bottom of the sample. Now, these reflected acoustic waves are converted back into electrical signals, and these signals are based off of subsurfaces on the sample. From these electric signals, we are able to extract properties that include material thickness, density, and interface. As we continue, we'll see that frequencies do play a role with these acoustic waves. They travel through a device at certain lengths, and they are able to pick up internal interfaces that include cracks, delaminations, voids, and air gaps within the sample. Now, nearly all production materials, including silicon, epoxy, die-attached materials, and metal lead frames, transmit ultrasound well enough to make these images that we'll go over shortly.
Let's take a look at the operation of SAM. SAM operates on reflection mode, works as follows. Transducer converts electrical signal into acoustic wave and insert it into the specimen. A certain amount of the wave is reflected back to the transducer and converted back to electrical signal. We can use the intensities and polarity of these signals to portray the interior of our specimen. Here are some important properties about SAM. First, we have the acoustic impedance. The impedance equals to the media density times the sound velocity in that media. Different material will have different acoustic impedance properties, and the physics behind wave reflection is closely related to it. The Galvin equation for wave reflection is here, where R stands for reflection coefficient. Wave propagates from material 1 with the acoustic impedance Z1 to material 2 with acoustic impedance Z2. The larger the impedance difference, in this case Z1 and Z2, the larger the reflection will be. Another characteristic of this post-echo approach is the depth of the interface inside the specimen. We can calculate the depth of the interface by using the time of flight, which is the time for the wave to travel from one interface to another, times the sound velocity divided by 2. Here is examples of the aforementioned operation. Our output is a time variant signal with time in x-axis and intensity in y-axis. We can see that first significant signal is the surface of our specimen, while the second one is the interior interface reflection. We can also see that the time of flight here, so we can calculate the distance or the depth of that particular interface. In this picture, we can see that when we scan the chip, we will get a shorter time of flight in the middle compared to the metal pad here. Let's say we are only interested in this certain area. We can use a gate at this region to filter it out if we want to. After knowing the physics behind acoustic, let's take a look at the setup for SAM measurement. Here we have our specimen submerged inside a water tank. This is because water acts as a good coupling media for our acoustic wave to travel through. Water is also uniform in acoustic impedance and form uniform boundary with the probe and specimen. Now we understand that SAM operates on the principle of propagation and reflection. But the next question is that what the difference will be. Here we have some numbers to show how things work out. Let's assume there's a crack inside our silicon die, which is our specimen. In this case, we'll have silicon with acoustic impedance 20. We call it Z1. And our crack, we assume is just air inside of it. With the acoustic impedance here, 0.00041. We'll take Z1 and Z2 into our reflection coefficient equation, and the outcome is almost 1, which is total reflection. Another parameter is the resolution of SAM. Key factor of this includes the following. Each one is linked to another, so I'll briefly explain it. We have our lateral resolution equals the wavelength times the focal length divided by the diameters of lengths. First, we have the transducer frequency. The higher the frequency, the higher the resolution will be. We also have the acoustic wave bandwidth. This one is related to the actual resolution. Attenuation also plays a big part here, since the higher the frequency, the more significant the attenuation effect will be. We also have to consider the probe design, such as the focal length. So for high frequency probe, we'll see that it has short focal length, since the high frequency wave attenuate faster than the lower ones. We also have to see that the diameter of the length, this one is related to the lateral resolution. Material absorption and reflection. Some material will absorb certain frequency compared to others, so this one has to take into consideration. Finally, we have the interface depth. The focal length is the length where the acoustic wave is focused, but in actual measurement, the length is actually shorter since acoustic wave travel faster in solid. You can see there's another cone shape here. So there will be a problem if the distance between our inertial interface and the internal one is longer than the focal length. That basically means that we cannot focus on the internal interface. Here we have the relationship of the frequency and other parameters. High frequency will have high resolution but short focal length and low penetration. Low frequency is vice versa. Here we have a table of transducer that could give us better understandings of the relationship above. In this case, let's say we want to penetrate with 2 millimeters. We will choose the probe with the frequency at 110 or 112 megahertz. If let's say we want a specific focal length or resolutions, we can see that let's say we want 100 microns in resolutions, we'll pick the 15 megahertz one. But in this case, the focal length is 19 millimeter, which is significantly longer than the 110, 112 we just mentioned. We understand the trade-off between frequency and resolution, but what kind of frequency is more often used? For industry non-destructive tests, we are seeing frequency range from 5 to 200 MHz, or more up to 300 MHz is not that uncommon. Beyond that, the trade-off between the penetration depth of the signal through the object and spatial resolutions has to take into deep scrutiny. Since the penetration depth will be that low, the application is quite limited, and you basically have to be extremely close to the specimen. There's also another problem with the high frequency is that it may require the pre-processing such as exposed dye, thinning substrate, or before the scanning. Those sort of things are not non-destructive, so it's not that common. Currently, there are research some applications that use up to 2 GHz, but that is not that common. So we talked about post-echo action from our previous slides. We make the example using single point, but making image certainly have to collect more information beyond just a point of data. So here we presenting the different scan mode for different type of imaging technique. We can see that here is the A scan. A scan is a single point, one-dimensional interpretation where signal is presented in time domain. The time between two pulses could be transformed into physical information. This is useful for getting the interior interface depth that we can use to set the parameter for other scan mode. Here we have B scan. B scan is a depth resolve cross-section image for the specimen. We have C scan. C scan is a surface scan for X-Y plane. Gate can be set to extract precise depth of the interest. Depending on the machines or the manufacturer, you might have X scan or Z scan. X scan is the stacked image of multiple C scan, and in this case, Z scan is a user-defined scan. You don't have to follow the X, Y, Z axis. Now we have talked about how SAM, the principles, and the limitation of it. The next question is, why use SAM? To be more specific, what's the advantages and disadvantages with SAM compared to other imaging techniques? Here we will focus on SAM and X-ray imaging since these two methods are common for industry. They provide reasonable penetration depth, allowing us to investigate the interior of the specimen without any pre-processing. Though numbers may vary between different machine models, SAM and X-ray has similar resolution and scanning time. So for SAM, we are seeing that it's not contact, so you don't have to be physically contact with the specimen while you're taking the image. It's really good at detection, crack or void or just general defect, interface difference, material difference, but the limitation is that the resolution is in micron range. You also have to consider the trade-off we just mentioned above, the resolutions and the penetration depth. It might have problems when you are imaging your specimen near the edge of your specimen. Another thing is that your sample has to be submerged inside a water tank. For X-ray have higher energy compared to the acoustic wave. So it's really good at penetrating, let's say, thicker specimens such as 3D packaging, where you have a lot of chips that stack together. However, the limitation is that X-ray, since it has such high energy, actually will damage the specimen. So, and it also has similar resolution in micron range. It has longer processing time compared to SAM. So here we have another comparison between X-ray and SAM. We can see that for lateral resolution, it basically operates in the same range. For the highest depth resolution, they're pretty similar. But the scanning time, we can see that the SAM is significantly shorter than the X-ray. We're talking about 2 to 8 minutes compared to 30 minutes. Let's take a look at some of these examples of SAM imagings. Here we have a SAM image of a MEMS sensor. We can see that a visible dark contrast at the edge. We use SEM image from the same location. It shows that a crack which start at the outer edge of the bond material and proceed into the area between the bond and the silicon track. On the right, the image shows interesting examples of a package undergo different imaging technique. We have SAM image on the left and X-ray image on the right. X-ray image shows that the wire and the metal pads are intact, which may seem to be a package with no defect. However, when we use the SAM, we can see that there are actually numbers of defects in this chip. We are seeing delamination, crack, and peeling on the lid. Next, void is one kind of defect that is not uncommon. Here we have examples of expecting cover field via of an interposer. In these examples, we can use the time of flight to get information such as the depth of the via. You can see there might be material above the silicon via. We could also get the thickness and shape of the via. In addition, we can get the ideas of the material that is inside the void. Let's say we have a void here. So how do we use these reflections to get those information? Well, the probe will receive the reflection signal earlier than expected if there's a void in present. The intensities of the reflection could also help us get the idea of what the defect is made of. So we can see the pictures on the right shows the SAM image of the via with and without defect. You can see on the top here is the ideal case where we have copper filled via, and here we have poorly filled via. You can see the intensity, the SAM reflection intensity is different. There are two different frequencies. We have 200 megahertz and 1 gigahertz were used. We can see the contrast between defect and non-defect one, and with 1 gigahertz you can clearly see the shape of the via as well. We could also use SAM to focus on the interface or metal connections. Pictures on the left shows underfill defect between chip and the substrate. The defect shows white area is on the top of the underfill, while dark area is at the bottom due to constructive and destructive interference. We can also use to observe micro cracks in integrated circuitries large area delamination as well. On the right, we can see the bound wire connections, with some of them appears to be delaminated. In this is confirmed with SEM image. You can see there is a not very clear delamination, a thin layer delamination between the bound wire and the substrate. Lastly, SEM has high enough penetration depth that could be used to examine chip-to-chip interface, not just bonding with solder balls, but also adhesive. On the right, we have SEM for PCB level delamination detection. We can see large area of delamination in the center of this PCB. This detection is made with millimeter dimension. Overall, we could see that SEM is a non-destructive way of imaging with a lot of application and with wide detection dimension from microns to millimeter range.
Thank you, Boe. Now we're going to talk about two different modes that depends on where the detector is placed. First, you'll see on the left there's the reflection mode, where the transducer is placed in water and the acoustic waves are bouncing off the sample and then detected with a detector near the transducer. On the other hand, on the right side, we have a transducer in the water that is producing acoustic waves that are going through the sample and then is being detected on the other side or the back side of the sample with a detector underneath it. As you can see here are some examples of transmission and reflection mode. I'll start off by saying that the reason to pick reflection mode in most cases is to evaluate samples at a high resolution. The reason to pick transmission mode is to evaluate materials that attenuate easily. As you can see here on the top left, there's the reflection mode, and we'll see that when an image has black, it means there's no reflection. When it's gray, it's weak reflection, and when it's white, there's a strong reflection. And this is all due to the difference in densities from the surroundings of the materials. As you can see on the bottom left, there's two examples of a die surface and lead paddles. You'll see that there's a reference part showing no white parts, and then there's on the right, you'll see failed parts in the corners of the die. And this is due to delaminations on the corners, resulting in the white spots. As you can see here on the top right side, in transmission mode, when there's a defect within the sample, the acoustic waves do not go through and is received on the other side, resulting into a black splotch, as you can see on the right. Again, on the bottom, there's a reference part and then there's a failed part. And the difference shows that there's a black spot right in the middle, and that is also due to delamination, causing blackness in the middle. On this slide, we have some samples provided by MuAnalysis. The top 5 samples were taken in reflection mode, and one of them has red in the center, and this is due to the software detecting delaminations, or a difference in pluralities. On the bottom, we have 5 samples that were taken in transmission mode, and 4 of the 5 are showing that they have been delaminated. After looking at all the features that can be detected using the SEM, I would like to tie it back to the application of looking for counterfeits. Now, counterfeits are samples that are either recycled, remarked, overproduced, defective, cloned, or tampered. And I'll be going over a few case studies that will show an SEM detecting things like ghost markings, difference in materials, and delaminations. Here we have an example of ghost markings that were detected in reflection mode. As you can tell, the original markings are behind the counterfeit markings that were on top, and the counterfeiter attempted to erase and laser etch the original markings off. On this slide, we have another example of ghost markings and an image that was taken at 50 MHz. Ghost markings are the result of a common counterfeiting technique that involves removing the surface coating of a used commercial grade package so that the package can be relabeled and ultimately deceive consumers. As an example here, we'll see that there is the original markings underneath the counterfeit. Now this seems very obvious at the moment with this image, but under visual examination, there is no evidence of the pre-existing or the original manufacturer's markings. At this time, there's no other procedures or known procedures that can non-destructively uncover what we see here. For our second case study, we see these 5 samples here that were all taken at 30 MHz. These parts passed incoming receiving inspection, high magnification inspection, and CT X-ray inspection prior to being analyzed on the SAM. As the SAM images show, there is black spots in the middle, and these black spots were not detected with visual inspection. Now you might be wondering what those black spots might be. Well, these packages had been etched, enabling erasure of OTP program memory, later filled with a similar epoxy, but due to the difference between the OEM plastic encapsulant and the film material, the SAM was able to detect it. For our third and final case study, we see an image here taken at 30 MHz. This image shows popcorn fractures, and they are indicated by these red arrows. Popcorn fractures are usually developed due to rapid escape of moisture that is caused by excessive heating, and this excessive heating is caused by fire that is used in counterfeit operations. To remove components from circuit card assembly boards, one common technique is to apply this fire and use a hammer to vibrate the parts off. In summary, the SAM is very useful for counterfeit detection. We see that in different scan modes that we are able to detect different things. In A scan, we are able to see incorrect dimensions and wrong materials. In B scan, we're able to see popcorn effect, delaminations, and wrong package material. And in C scan, we're able to see ghost markings, wrong package material, popcorn effect, and delamination. In the end, there are multiple companies and vendors that can provide SAM solutions. Sonics, Alter Technology, Norton Sonoscan, Mu-Analysis, and Hitachi Power Solutions provided material that were used in this presentation, and I want to thank them for allowing us to do so.